In this video, I would like to show you how to create a model of a kind of a diffusive wave hydrodynamic model, one-dimensional hydrodynamic model of a kind of stretch of a river or stream, if you want, or open channel using GIFMod. So this is the diagram of the model that I would like to create. So it's not, of course, it's not up to scale, but we have in GIFMod you can model basically channels with kind of rectangular cross-sectional area. We can also use, channels with kind of irregular cross-sections, but then we have to use rating curves, which I'm not going to talk about in this video about. So this is the diagram of what I'm trying to model. I want to model a 5-kilometer stretch of a stream or a open channel. I will basically discretize it into 10 segments. Now here I'm showing 6 segments, but in reality I'll do 10 segments. So each segment will be 500 meters. The width of the channel is going to be 5 meters. I'm going to use the Manning roughness coefficient of 0.015, and the slope of the channel. So basically what I will do is that I will let the elevation of the bottom of the channel to drop from 0 to -1. Okay, so basically we have a 1 meter drop in 5 kilometers, which is going to be 1 over 5,000, a slope of 1 over 5,000. And then I'll apply this inflow to basically our upstream boundary condition. So I'll have a time variable inflow that will go from, so it's going to be 10 days simulation, and my inflow will go from 100,000 to 200,000, and it will go back to 100,000. And then for the downstream, what I'm going to do is that I will consider a fixed head boundary condition. So I'll assume at this, the lower boundary, my hydraulic head is going to be fixed, and it's going to be equal to -1 meter. So GIFMod uses diffusive wave model to simulate the flow. Okay, so let's get started. So I'm going to start GIFMod. So here's what I'm going to do. So this is a GIFMod window. So what I'm going to do is that I will create one. I'll first create one stream segment block, and then I'll try to assign all the properties, and then I'll make an array. So that way it's going to be much faster. So let me add my stream block. So this is my stream block, and then let's go ahead and assign some of the parameters. So the bottom area, of course, if you look at the diagram, we have, for one segment, we have a length of 500 meters and a width of 5 meters. So the area will be 2,500. Okay, so I'm going to assign that 2,500. For this block, I'm going to set the elevation to be 0. So that's going to be my upstream segment. And then I'll show you how to make the bottom elevation to kind of gradually decreases or linearly decrease when we create an array. So the initial water, this is going to be our initial condition, which I don't know. Now you can use Manning's equation to calculate what's the initial condition based on the initial flow, but I'm going to just assign, I don't know, an arbitrary number, and we'll find out later on whether it's a good initial condition or not, and we can go and probably modify that later on. So then the Manning roughness coefficient, as I mentioned, I'm going to use this number 0.015, and then the width, of course, is going to be 5 meters, and the length is going to be 500 meters. Okay, so that's going to be 500 meters, and I think that should be pretty much all I need. So now what I can do is that, let me just save this. I'm going to save it as, I'm going to save it as stream model. Oh, Okay, yeah, that's it. So basically now what I'm going to do is that I will just create an array. So I just right click on my block and I click on make array of blocks. I'm going to go with horizontal two-dimensional. Even though the vertical two-dimensional will work, we only have one row. Then here, this is supposed to be number of rows. On the Linux version, it somehow it doesn't show the full text of the label. So this is going to be number of rows, which I'm going to say, oh, that's actually number of rows is going to be 1. Number of columns is going to be 10. And then something I got to be careful about is basically the total bottom elevation change in x direction, right, is going to be -1, right? So basically the bottom elevation will decrease eventually by -1 meter, actually by 1 meter. So, and then everything else is good. So I'm going to just click on OK. So this is fine. And if you look at the bottom elevations, you'll see that it goes down by 0.111. And then at the end, my last block, I'm going to have, I mean, there's some rounding issues, but it's actually -1. So now I got to do two things. First, I want to apply the upstream boundary, which I'm going to use an inflow file in order to do that, and then I need to also set the downstream boundary. So let's do the upstream boundary first. So I need an inflow file. I need to create an inflow file. So let me go to my text editor. Of course, you can use any text editor that creates ASCII text files. And if you're familiar with the inflow files, we need a names flow. So we are only going to have specify flow in this inflow file. If you have if you want to do water quality modeling and have other water quality constituents and so on, we can include them here too. But I only have flow. So then I have a time. So as I said, basically at time, this is what I want to do. At time 0, my flow is going to be 100,000, and at time 5 days, it's going to be 200,000. It's going to go back to 100,000 on day 10, right? So basically 0, 100,000, 5, 200,000, and then 10, again 100,000. So that's pretty much it. I'm going to save this. Let me save it in my documents, even though that's not the best practice. So I'm going to say inflow channel example.txt. So that's going to be the inflow file that I created. I can probably close this. Go back to my. So now I just click on the upstream block, and on the inflow time series, which is basically this property right there, I just click here, and then I pick the inflow file name that I just created. This is it, inflow channel example. This is the file that I just created. Now to make sure that everything is working fine, I can just right click on the block and then pick plot inflow properties, and you see that we only have this variable flow, and this is it. So we start from 100,000, goes to 200,000, and then goes back. So that's my flow. That's my upstream boundary condition. Now the downstream boundary condition, what we do is that we add this dummy kind of it can be a pond or it can be a stream segment. What it is I just add a dummy block, and then I fix the head, the hydraulic head, okay, so that the hydraulic head remains constant. I'm going to use a pond, so I'm going to add this pond. Just added it here, so I'm going to drag it. Maybe, I got to zoom out, and I'll just add it here. And then so I need to provide a bottom area, which it's not going to be used because I'm going to fix the hydraulic head, but GIFMod is going to give me an error if we have a pond block without the bottom area. And the bottom elevation, it doesn't really matter. So I'm gonna leave it. The only thing that I need to change is there's this. So by default, the head storage relationship is calculated based on the the governing equations considered for the pond. But if I want to replace that, and basically if I want to make sure that the head will remain constant regardless of how much storage we have in the pond, then what I can do is that I can just type the value for the head storage relationship. You can type it formula too, but in this case I only need the value. And as I said, I'm gonna set this value to be -1. So that will do everything for me. Let me make sure the initial water depth is here is fine. So now the next thing I'm gonna do is I will connect this last stream here, and then I'll attribute the same properties as other connectors. So what I'm gonna do is that I'll assign a Manning roughness coefficient of 0.15. I'll assign a width of 5 meters, and then I'll assign a length of 500 meters, right? So 500 meters. Okay, so that should be it. My model should be ready. I'm gonna just save it. Oh, by the way, I forgot one thing, and that is I need to change my simulation period to 10 days. So by default, it's 1 day. The simulation start date is 0. I mean, time is 0, and the simulation end time is 1. But I can just change this to 10, let's say, and I think we should be ready to go. Okay, so that's it. And now let's look at some of the results. So what I'm going to do is that let's look at the water depth at this last column. Water depth. So as you see, my initial condition was a little off. So we have, we see that the water depth ranges around 0.9 to 1.1. So I started from 0.5, which was a little off. Then so that's it. I can look at the water depth, let's say at this upstream block 2, and then in this case the wave moves really fast, so there's not that much difference between the water depth. The length of the model essentially compared to the speed of the wave is kind of small, as you can see. Oops, yeah, so basically the shape of the waves are the same, but so this is the situation that I would get. I can look at the flow. So if I click on the links, I can look at the flow. So this is the flow going from block number one to block number 2, and then I can look at the flow maybe just leaving my system, and they should be pretty close to each other. Yeah, as you can see, there's a little bit of delay, but anyways, and that's pretty much it. Now I can do some other visualization too. So for example, I can look at the water depth as it basically varies throughout the simulation. So because of the fact that I set this -1 fixed head, the water depth at the downstream block is lower than the water depth at the upstream one. Or I don't know, I can also look at, let's say, for example, hydraulic head again. So that's how hydraulic head changes, and so on. And that's pretty much it.